This lecture is concerned with continuous modeling and the first lecture on continuous modeling. Um, Continuous modeling, we're going to look at these topics in this first part. The organization for continuous modeling in Visual SLAM, collecting time persistent statistics on state variables, S-event input statement, a detect nodes, and continuous control model statement. All of these are new features that are typically used in continuous model. In a continuous model, you have what's called state variables. So most of the model itself is reflected in these state variables, and in Awesome or SLAM, these are called SS variables. We can also reflect or represent the changes in a state variable by a derivative equation, and that's called a DD variable. In Awesome, you represent each state variable in one of these two ways, but not both. If you represent it as a DD equation, Awesome will take care of integrating that derivative equation and calculating the value of the state variable. This is the structure. The main thing that's added here is function state. Function state is a function you write to define the SS and DD equations, and then Awesome will use that function to automatically update the values of the state variables and perform the integration and time advance functions. To give you an example, let's talk about the Cedar Bog Lake problem in your textbook. This is an illustration. On Learn, we've also included a project folder for this particular example. In this case, we represent an actual lake that exists in New England called Cedar Bog Lake. And we're going to represent several state variables. Here you see them as X subscripted variables. X sub S, for example, is the energy of the sun that comes into the system. So down here at the bottom you see the equation that represents how this changes over time. We assume a sine wave effect, and all of the coefficients and so forth that convert this into a standard representation of solar energy. Plant energy is reflected as X sub P. It's a function of solar energy, which causes the plants to grow, minus a death rate for plants. This is calculated from data. We also have herbivores, which are a function of plants and the death rate of herbivores. Herbivores eat the plants, of course. We have carnivores that eat the herbivores, so they have a positive effect from herbivores and a negative effect from their death rate. Omnivores is a function of both plants and herbivores and carnivores. The carnivores, the energy rather, at the bottom of the lake is reflected in terms of elements that fall out of the system. This increases as a function of plants, herbivores, and carnivores. At time zero, we have the initial concentrations in energy units of all of these variables. So we're going to represent each X subscripted variable by an SS variable, indicating that it's a state variable. But some of these will be represented in terms of how they change as a function of their derivatives. So we will actually represent them in function state as DD variables. So we have 5 of those, and then the last one, SS6, is the solar radiation variable, and it's just a direct function of a sine wave. The rest of these must be put in subroutine state first. All of the DD equations, in other words the state variables that you're going to represent as derivatives, must be numbered 1 through however many of those that you have. After that, then you start using the SS variables with whatever subscript is appropriate. So all of these DD variables represent derivatives of plants, herbivores, carnivores, omnivores, and the a collection of energy at the bottom of the lake in terms of sediment. So function state looks like this. You'll need a vslam.h statement for include. You also include the math.h library, which is standard with C, and any other variables. We're going to define pi here as part of the sine wave calculation. So we've numbered 1 through 5 DD equations, and then SS6 is put first since it's independent of any other state variable. After that, the DD equation, DD1 is a function of SS6 and SS1, and so forth. So basically you just kind of line things up. You number the state variables 1 through 5 in this case for DD, in other words variables that are expressed as derivatives, and then SS6 is the last, but we have to put SS6 here since we're going to use it in one of the subsequent equations. All of these variables can be included as time persistent statistical collection. So we can reference either an SS variable or a DD variable, and then we just put them into the timestat statement in the control model, just like we do other timestat variables. Another input statement in the control model is the S-event model. This or statement. This is analogous to the detect node in the network portion of the model. It's used to monitor any kinds of state variables or other system variables and trigger what's called an event or a state event when we have a crossing of a threshold by any of these state variables. This causes a call to function event with an event number specified, and then you have to program what happens as part of that event. So we can use this S-event to detect when a tank is full or empty. So we would initiate a change in the state of a valve. When we've reached an altitude, we're simulating an aircraft, we would stop applying power to the engine and level off. The detect node, you've seen that before, is used in the network portion of the model to do pretty much the same thing. So the detect node sits there and monitors whatever you've asked it to, and then after that the detect node is initiated, and an activity, or an entity rather, is scheduled to occur flowing out of the detect node. We also have another new control model statement called the continuous statement, and this is used to set error levels and step size for integration. So we have an absolute and relative error as well as a step size error. I can start up Awesome and show you this particular statement. This is, and some of these parameters are basically required that you kind of guess at their values. So for example, in the Cedar Bog Lake model, if we open up the control model, you'll see the continuous statement here. In the continuous statement, you have to specify how many differential equations you have. Those are the DD equations, and how many state equations, or SS equations, that you have. So in the Cedar Bog Lake example, as you recall just seeing, we had 5 DD equations and 1 state equation. Time step size refers to the integration routine in which we integrate these differential state variables, and it refers to the size of the time step that we take. If we take too big a step, we might accumulate too much error, and Awesome will automatically have or reduce the step size. We also are permitted to specify the absolute and relative error that we allow in the integration. So this is Awesome has some procedures for estimating error, in deciding how to move forward in time and calculate new values for the state variables. In this case, we have assumed an absolute value of 0.025. So anytime the error exceeds that, then we will reduce the step size and take a smaller step with the hope that we can get a more precise estimate of the state variable. So this control statement is required in all of the continuous models. This last slide refers to what happens when we have simultaneous state events. Sometimes you can have multiple crossings of a threshold, and those might occur at the same time. So this function can be called from your user code to detect whether you've had a state event occur and what state event. Each state event has a unique number, and then returns these values, whether there's no event, it's a positive crossing within tolerance or outside of tolerance, or a negative crossing within or outside of tolerance. So it's useful for detecting simultaneous state events, which may require different processing than if those state events occur separately. We can take one more look at the Cedar Bog Lake problem and look at how the output, essentially just click update to run the model, and in this case we don't have a compiler, so we'll take a look at the Cedar Bog Lake in the next video lecture.